Hello, everyone. My name is Fan Jiang from Xiling Software and AI Technical Marketing. First of all, thank you for participating in this webinar, especially at this tough period. I wish all the best to you and your family, so just stay safe and healthy. Back to this session, it will be a deep dive of Vitis AI. If your interest or application is AI related, I hope this session works for you. Before we get really deep down to the details of Vitis AI, it would be good to give a definition first. So what Vitis AI is. And to my experience, when I give presentations about Vitis AI, the most questions I've been asked is like, do I need to install Vitis first to enable Vitis AI? The answer is simply no, you don't have to. Then the following questions were more like, then what's the relationship between Vitis AI and Vitis? Okay, so today we can just start from here to talk about Vitis first. Vitis is a development kit for software developers to do hardware development. The traditional FPGA users are more hardware developers. They know FPGA well, they know RTL, they know how to use the hardware programming languages like VHDL, Verilog to do FPGA programming. And today, we're trying to enable more software developers to program FPGA. No matter you are doing front end, doing back end, no matter you are doing embedded software or doing application level software, you can all use the Vitis development kit to program FPGA. And in order to make the Vitis more software developers friendly, we have provided a series of advanced libraries. For example, the vision libraries, the finance libraries, and Vitis AI is simply one among them. Actually, Vitis AI is more than some advanced libraries. And I would like to define it as the title here, the Unified AI Inference Solution Stack. The unified here could be extended from two aspects. The first one is unification of the framework. Currently, Vitis AI supports Caffe and TensorFlow, which means no matter your application you're doing, no matter what kind of model backbone you've used, and no matter what kind of data set you have trained, as long as you belong to Caffe or TensorFlow, you're able to use the Vitis AI to do quantization, compilation, and implementation. The second aspect is unification of the platforms. I don't know how many of you have used the DNDK or XFDN before. They were totally different architectures. And DNDK is the official solutions for the edge platforms, while the XFDN is for cloud. And they have been unified now, and both under this Vitis AI brand. And 2 weeks ago, we have released the Vitis AI version 1.1, and the PCIe board U50 has joined the Vitis AI family. So now, for PCIe boards, we have support U50, U200, and U250. The Vitis AI, from top to bottom, could be distinguished into several parts: the model zoo, the AI quantizer, the AI compiler, AI library, AI profiler, and DPU. And in the following slides, I will do a more comprehensive introduction to each of them. The model zoo contains 50 models altogether from both TensorFlow and Caffe. It is totally open and free for all developers. The motivations for us to release the model zoo could be summarized into 3 aspects. The first one is fast implementation. The model zoo contains the quantized model, which could be compiled directly and deploy on board. It allows the users to get a first impression how the AI could help in their application before getting their hands really dirty on the new tool, or they could directly use it in their own design without any legal issues. The second one is also important. The model provided here are all state-of-the-art and well-trained with public datasets. Users could easily reproduce the results or take it as the baseline to retrain the model with some private datasets. All the training scripts, along with super parameters, are provided as well, which could avoid the users to do the job from scratch. Last but not least, the model is provided with the evaluation script and benchmark on different platforms. Users who have clear demands can easily filter out the qualified models by simply looking up the table. The model zoo table lists the entire model names and the framework they belong to, the backbone architecture, the input size, the OPS per image. OPS here stands for the operations. It represents the complexity of the image, and also the training datasets, validation datasets, extra. For each model you downloaded, the repository looks like the bottom screenshot. The most important file here is this readme.markdown. It contains all the useful information of this model, including the input-output names, and also pre- and post-processing extra. And also in this repository, you will find the float model, which is the baseline, and the quantized model, which is ready for deployment. And also, the inference scripts of both float and quantized model will be provided here as well. No matter you choose models from our model zoo or use your own customized model, the quantization is compulsory, as the DPU only supports 8-bit computation. And the AI quantizer here will convert the model from float point 32 bits to integer 8 bits. The input of the quantizer will be the float baseline model along with a calibration dataset. The calibration dataset usually contains hundreds of images from test dataset. It is used to define the dynamic range of your input. The quantization itself doesn't need backward propagation, only forward. However, a test will be performed after the quantization is done. And if we observe a large accuracy drop, then the quantized fine-tuning is required. The fine-tuning is more like a retrain progress, so the training dataset needs to be involved. After several iterations of fine-tuning, it will be finished when the accuracy is pulled back to an acceptable range. Then the model will be converted to an intermediate representation and then compile and deploy on board. At this seminar, I can't really share my desktop and do a lab demo, so I have to copy and paste some command line script here and to explain what happens. Oh, by the way, the Vitis supports both GUI and command line mode, but for Vitis AI, only command line mode is supported. So here, VAIQ TensorFlow quantize is the keyword, and followed by several parameters we need to set. The first one here is the input frozen graph, which is the baseline input. Okay, and the input F1 is the pre-processing. If you get the customized models, you might have some specific pre-processing other than some mainstream networks. So that need to be defined here in this Python script. And then the output directory, the input nodes, output nodes. Why we need this input nodes, output nodes? Because sometimes the pre-processing or post-processing will be combined with your model structure, and that part needs to be separated. So we use these input nodes, output nodes to define the backbone of the network. Okay, the input shapes. This question mark doesn't mean not known, but this channel dimension will be defined in the input element. And the last one is the calibration iterations. By default, it will be 10. So if you got a large calibration data set, you don't have to set a very large number, and it will be pretty enough. And after the quantization, if fine-tuning is not required, it will take about several minutes, won't too long. And after it's done, you will see a quantization summary as the figure below here at the bottom. The AI compiler, so after the quantization is finished, we get a quantized model of integer 8 bits for both waits and activations. Then we need to use this AI compiler to convert the model from a quantized to the instructions, which our CPU can understand. It would be good to point out that this AI compiler is hardware dependent, which means you need to assign a specific platform to where you want to deploy on. Okay. Previously, we have stated that our Vitis AI supports unified platforms. So it could be deployed on either the MPSoC or the ARVIO. But actually, the IPs on MPSoC and ARVIO are totally different, because MPSoC is a heterogeneous platform. We got ARM inside, and ARVIO is just pure logic, right? So that's the reason why the IP is different. So the IP is different means the instruction side will be different as well. Okay, so that's why here we need to assign so which platform we want to deploy it on. So then the compiler could generate the instructions correspondingly. And here, if we look at the detailed command line here, so we will define the target platforms. Here is this U2, is the Z9-based evaluation board. And then the night name, here is ResNet 50. Actually, it could be anything, as long as it's a good hint for you to remember so which network you're currently compiling, right? And then the deployed, the output path directory. And the most important thing is here, so there's a JSON file. It contains some hardware information which will be generated during the hardware integration process, no matter using Vivado or Vitis. Okay, so after this compilation is finished, you will see a summary table like the figure on the bottom right. It will state your kernel name, your model size, parameter size, and working loads, etc. Okay, so this information is required on the deployment stage. And some people may ask, you got different IPs on cloud and edge, and you got instructions different on cloud and edge, then how you could achieve a unified platforms in Vitis AI? The answer is in the runtime level. Okay, we got unified runtime. So all the Linux devices has been managed by the XRT, which stands for the Linux runtime. And above XRT, we got Vitis AI runtime. And here we define 5 runtime APIs: the execute, the wait, get tensor formats, get input tensors, and get output tensors. Okay, these 5 APIs will be enough to deploy any deep learning models on CPU. These APIs may not give you the best performance, but it will help you on the early phase when you're not sure which board you're going to use, or which chip you're going to use, or even which CPU architecture you want to apply. You can simply use the same deployment codes and reuse it on any CPU platforms. Okay, all you need to do is recompile the model with AI compiler. Okay, here is the code fragments for how we're going to deploy a ResNet 50 network on DPU by using this Vitis AI runtime unified APIs. So I won't explain the code line by line, but I will definitely show you some key architectures of this deployment. At the very beginning, we define the model directory here. The model is the instruction set is the output of the AI compiler. And then we will create a DPU runner. So each DPU runner will combine with one DPU core, which means if you got 3 DPU cores in your platforms, so it would be better to declare 3 DPU runners. Okay, otherwise, if you run your task with multi-threads, they're all running on single DPU core. And the middle part will be several tensor declarations. And then will be the pre-processing. Okay, we use the vision libraries to read the images in and do some computations like mean subtractions, the normalizations of the image crop, etc. And then we use this execute APIs to run the models on our GPU. Then the post-processing. Okay, we use these APIs to get the results from the GPU and to post-processing. So this is the typical deployment architectures that could be applied on any deep learning networks. The Vitis AI runtime more focuses on unification across platforms from cloud to edge. And above that, we have Vitis AI library, which provides some application-based high-level APIs, which more focus on the ease of use and optimization. The most important thing is the codes are fully open source. So if your application or area of interest has not been included in our library, you could also refer to the source code and develop your own. The general process of AI application is shown here. So first, we got sensor output. For a typical vision-based task, the sensors usually be a camera. So after that, we have some system-level pre-processing. Usually be the video stream encoding and decoding. And then we have some algorithm-level pre-processing, like the normalization, image recess. After that, the model has been deployed on the DPU for computation. And output will do some post-processing from algorithm level, and then some system level post-processing. So that's the typical workflow for general AI application. And among this, so which part the Vitis AI library could help is the areas inside these pink boxes. Okay, the Vitis AI library will provide algorithm-level end-to-end acceleration. The deep blue part, the pre-processing and post-processing for edge deployments will be running on ARM processors. We could apply some technique like zero copy or neural acceleration to make it running faster. And we'll also provide some hardened IPs if the software acceleration doesn't work well. And the red part in the middle will be running our DPU. The Sonic's advanced scheduling technique will make sure the DPU is running with high efficiency. Okay. With all the parts cooperation, we'll provide an end-to-end optimized solution. And now let's look at some details of the AI libraries. So as stated previously, the bottom of the AI libraries would be the runtime level, the status runtime and the Vitis AI runtime. And above that, we have some base libraries, like the DBMap, the XN post-processing. They contain some base mathematic libraries and some typical post-processing techniques here.
And on the top level is the algorithm libraries. So we get classification. So no matter which backbone you have used, no matter it's a RESTnet, it's a reception, it's a mobile net, it's a SqueezeNet, because all the pre-processing are very similar and the post-processing are exactly the same. So they could be combined together as a single category. Similarly, we got segmentation here is just some pixel level classification. And for detection networks, we got both SSD and YOLO because they are post-processing different. So we have to separate them to two categories. You could also see like phase and row line here. So they are more application-based, not algorithm. Usually for phase related, we got the tasks like face detection, face recognition, and Ray ID, extra. So which means the network usually needs to extract some secondary attributes that are more complicated tasks. So we use category to define all of them. And similar for the row line. And for each categories, besides the well-trained and compiled model, we have provided 4 kinds of test examples: the test JPEG, test video, test performance, and test accuracy. The input of the test JPEG will be a single image, and the input of the test video will be a video clip. These two are used for quick validations. You can input either an image or video to see if the bounding box is correct or whether it has been fall into the correct class, extra. And the test performance, you could either use true validation datasets, or you could use a single image and run it in loop 1,000 times to see the end-to-end performance. And for test accuracy, we need the validation dataset with annotation here. Okay, and we need to define the evaluation matrix properly to see the accuracy of the model. And they just need to be aligned with the float baseline model to see how the accuracy changed. Let's see an example of how we use these high-level APIs to deploy a UV3 and run with this test JPEG API with a single image input. Okay, so we could first look at the bottom right. Because this is high-level APIs, the code is pretty structured. All we need to define here is the name of the network, which is UV3. And then if we look at the bottom left, this is the image output. We can see 4 green bounding boxes to detect the vehicles. Okay, and the top image will be a running example. Okay, we use this test JPEG APIs and followed by the image name, and then we got 4 outputs. Result 6 means the class of the vehicles, and then the number following is XY coordinates of the bounding box. All right, as the AI library is the most essential part of the Vitis AI, let's just do a quick summary here. Okay, the first one is seamlessly compatible with AI Model Zoo. For AI Model Zoos, each model has been published with a benchmark on different platforms, and it will be easy for users to reproduce that result with our high-level APIs. And the second one, samples for fast prototyping. So if the user is just got the initial idea and haven't go deep down to the model selection or platform selection, so it will be good to refer to our Model Zoo and AI library first. So you may find something useful there. And the third one, so high-level APIs to deploy the algorithms. Because in our model zoo and AI library, we have applied their own mainstream models. So it's more than likely that users have used the same model, but maybe trained with different data sets. So all the user need to do is to modify the pre-processing part, maybe the image resolutions, the mean value, the scale value, and that's all of it. Then you could still use our high-level APIs to deploy the model. So it's pretty fast. So that will very benefit the users in the early stage. They don't need to waste the time on the two-chain cells. They could see the results pretty quick. Okay, the last one, support multiple deploying approaches. The Vitis AI runtime APIs, they are fundamental APIs. Users could always refer to that to build up their own applications. And we have also provided the AI library high-level APIs. Users could use that to achieve a higher performance. Because the high-level APIs, they are completely open source. The users could also modify from that to build up the application. They're all supported. AI Profiler. AI Profiler is a set of tools that helps profile and virtualize AI applications based on Vitis AI libraries. It's a very important tool, especially during the optimization or troubleshooting stage. They could help the users to find out the bottleneck of the current workflow. The AI Profiler could be distinguished into two parts. One called AI Tracer, the other called AI Profiler. AI Tracer is running on the target devices. The users doesn't need to recompile the program to get it done. And the generated profiling results will be saved as .xat files. It could be sent to the local server to observe. And on the server side, when we receive this XAT file, we could simply open up a web browser to see a virtualization result of the profiling. Here is the example of the virtualization results of AI Profiler. Let's look at the top part first. The platform is the ZC102. So F3, we got 4 ARM cores here, and we have integrated 2 DPU cores. For CPU core, different color here indicates different tasks. And for DPU, when it's occupied, you get color here, and when it's idle, you will see a blank. So users could easily find out the DPU and CPU running efficiencies. And the middle, there will be an end-to-end throughput in the union of FPS. So if the computation is the bottleneck, users could easily find out which core have more bandwidth and which core is running with full bandwidth. The bottom part will be the traffic of the DDR. Sometimes the bottleneck of a program doesn't happen at the computation stage, but at the transportation between the DDR and the processor. So the DDR traffic is observed as well to help the users to have a general idea of how this program performed. Okay, now let's get down to the hardware overlay to talk about the DPU IPs. The DPU IPs is provided in the format of a TRD. Well, the TRD stands for the Target Reference Design. The first goal of the DPU TRD is to demonstrate a step-by-step workflow and how to integrate DPU as a kernel. The ZC102 platform is applied as a reference here. And besides the reference project, the pre-built files are provided so that users could do validation when finished. And secondly, the TRD contains a fully configurable IP which could be adjusted to fulfill your own design. The TRD not only shows demo how you could do it, but also tell you why you need to do that configuration, which means it shows the integration flow in an optimized way. The third one is about Vitis. Vitis is an innovative and powerful tool for software developers to do hardware FPGA design. So the TRD shows this new published evolutionary integration progress to users who may not be familiar with Xilinx devices. And the TRD architecture is shown as the left figure. The RTNL kernel is the most essential part here. The apps will be some models and related libraries which will be applied after the integration is done. Is used to quickly do the validations whether the IP has been integrated correctly. And in the project, we have both Vivado and Vitis project provided here, along with the pre-built image and configuration files. Users could select freely whether to use the Vivado or Vitis flow. Last but not least is our demo zoo. Xilinx has provided a series of demos at different application scenarios. On the left-hand side is an ADAS demo. So we could use a single network to achieve both detection and segmentation. And we can also achieve 4 channels, with each channel 25 frames per second, plus 1 channel for the road line detection, also in the real time. On the right-hand side is the multitask plus post-detection demo. It used to demonstrate a low latency of our video processing. On the bottom part is the original videos, and the top part is the video after processing. This network has also been used in the ADAS scenario. The detection plus segmentation used to detect the road scenario, while the human gestures used to detect the people in cabin. And that's everything for the presentation. Thank you for listening. Users could download the Vitis AI tools through the link on the screen. And next, I will show you short videos to help you work through the utilization of the Vitis AI tools.
Hello everyone, this is Fan Jiang from Xilinx Software and AI Technical Marketing. Today, I will briefly introduce the utilization of Vitis AI tools. In the XDF Beijing 2019, Xilinx officially released the Vitis AI version 1.0, which is a full-stack software toolchain dedicated for the development and optimization of deep learning algorithms on a unified Xilinx platform. Users could either download by clicking the link on the Xilinx website or directly from the GitHub repository. Now here we start. The first step will be the tools installation. To reduce the dependencies of OS and third-party libraries, the version 1.0 of Vitis AI adopts Docker images for the release. In addition, to adapt to the working habits of software developers, only command line format is supported. Users could simply use git clone command to pull the repository from GitHub in Linux environment. The progress will take a few minutes. Afterwards, we could see the Vitis AI folder in the current directory. Enter the Vitis AI folder. If it's a CPU server we could directly enter the Docker container by using Docker run script. Or if it's a GPU server, we need to enter the Docker folder and run the Docker build script to build up the GPU Docker image. Built successfully, the processing time may vary from 20 minutes to several hours, which is relevant to the internet and the local environments. The GPU Docker running procedure will be the same as CPU Docker from now on, and I will take the GPU one as an example. The example I show here is based on a ResNet 50 network under TensorFlow framework. Using Docker run script followed by GPU Docker parameters to start. Then, user could see the big Vitis AI logo on screen. As the ResNet 50 here is under TensorFlow framework, we need to enter the TensorFlow Anaconda environment. Inside the ResNet 50 folder, the float graph contains the well-trained floating model with .pb and .checkpoint extension. The first step here is to use the freeze script to get the frozen graph. The script here is provided by the official TensorFlow maintainer, and we only need to define the input graph and output graph. After frozen, the graph is still in float points, but all the weights converted from a variable to constant, so the weights don't update during the quantization progress. We could find the output graph within the frozen graph folder. Now we could start the quantization. Let's see the script here. VAIQ TensorFlow is the name of the binary, followed by the keyword quantize. We need to assign the input graph, input nodes, input shape, and the solution. Output nodes, data augmentation methods, quantization method, GPU card number, calibration number, and output directory. The calibration number is set to 100 by default. It could be adjusted based on the number of calibration images and model complexity. When finished, we could find the output in the quantized graph folder. The next step will be the model compilation. The compilation is hardware dependent, so we need to assign the platform here. Let's take ZCU102 as an example. In the script, we need to give a name to the model. Assign the GPU architecture here. The JSON file will be provided with Xilinx platform, and it could be generated by our tools after hardware integration for customized roles. Assign the model directory, output directory, and VIC TensorFlow is the binary of compiler here. Execute the script. If the model contains the operators that are not supported by DPU, user will see the warning messages as displayed. These operators need to be deployed manually on CPU. Compilation completed. A summary will be displayed on the screen, including parameter size, complexity, memory occupied, and input-output dimension. User could find out the output in the ELF output folder. The work inside GPU Docker is completed. And let's switch to the runtime Docker for the hybrid compilation. Please use exit command to exit the Docker. It will be the same progress to start the runtime Docker, but simply change the keyword from tools to runtime. After entering the environment, we could see several files in the ResNet 50 folder. SRC folder contains the C++ or Python codes, which defines the pre- and post-processing. Users should copy the .l file into the model folder. DPU v2 run directory has some hardware-related configuration inside. After copying the L file in, let's recompile the project. The progress will take tens of seconds. Then, user could find an executable file generated. Afterwards, user only need to copy the executable file, inference image, and image label to hardware platform for inference.